Consider this logarithm. Log base 36 of 216. Now if you put that in your calculator, it's pretty clear that this is a rational number. It's 3/2. On the other hand, if you look at log base 2 of 3, this one certainly looks to be irrational. Of course, keep in mind that looking at a finite number of decimal places does not confirm that it's irrational, but it's a good reason to suspect that it's irrational, at the very least. So my question is this: when are logarithms with a natural base and a natural input rational numbers? When are they irrational numbers? When are they transcendental numbers? Let's find out. I think the best way to approach this question is to look at a few examples of these seemingly irrational logarithms and prove that they are in fact irrational. In doing so, we should be able to find the little thing that happens, for lack of a better word, that makes these logarithms fail to be rational numbers. Now, proving that a number is irrational is of course proving that it is not rational. So a proof by contradiction is pretty natural here. So let's suppose log base 2 of 3 is equal to a ratio of natural numbers. Alright, now from that statement, we can use the change of base formula, whatever you want to call it, and we get that natural log of 3 over natural log of 2 equals a over b. Alright, and from there we can say that b times the natural log of 3 equals a times the natural log of 2. And then from there we can exponentiate both sides with a base of 3, e, and oh wait, those are the same, aren't they? Okay, I'm just kidding. Okay, so exponentiate both sides with a base of e, and we end up getting 3 to the b equals 2 to the a. And this is actually a contradiction. Do you see the contradiction here? Well, these are natural numbers, right? A and b are natural numbers. So this is even, but this is odd. So we have an even number equal to an odd number. That's a contradiction. And so that shows that log base 2 of 3 cannot be expressed as a ratio of natural numbers, as doing so implies a contradiction. So log base 2 of 3 is in fact irrational. Alright, let's look at another example to try to get a little more insight on this. How about log base 6 of 12? If you put this into your calculator, it again certainly appears to be irrational. So let's prove that it's irrational. We'll proceed the same way. Alright, well, I did the last one, so I'll give you a second to pause the video and find the contradiction that arises when we express log base 6 of 12 as a ratio of natural numbers. Alright, time's up. So, going from just as before, we can use the change of base formula, or whatever, and we get natural log of 12 over natural log of 6 equals a over b, the ratio of natural numbers. By the way, I'm picking natural numbers instead of integers because we know log base 6 of 12 is positive. So without a loss of generality, we can say a and b are positive integers. Just wanted to mention that. Alright, so from here, we can say that b times the natural log of 12 equals a times the natural log of 6. Alright, now we can exponentiate on both sides with a base of e, and we get 12 to the b equals 6 to the a. Alright, now this is not immediately a contradiction, but the next thing we can do is use the prime factorizations of 12 and 6 and see what happens. So 12 is 2 times 2 times 3, so we get 2 to the 2b times 3 to the b equals 6 is 2 times 3, 2 to the a times 3 to the a. Alright, and this implies that 2b equals a and b equals a. But if b equals a and 2b equals a, then b equals 2b, and so b is 0, but then a is 0. That's a problem because log base 6 of 12 is equal to a over b. That's how we started this. And in conclusion, a and b are both 0, so that's an indeterminate. So this shows that log base 6 of 12 cannot actually be expressed as a ratio of natural numbers. So log base 6 of 12 is irrational. Alright, so based on what's just generally happening here, we can say the following. For any two natural numbers, log base m of n is rational if and only if there's an integer solution for the equation m to the a equals n to the b. So there's an integer solution to this exponential equation here. Now, I don't know about you, but I don't find this very enlightening or intuitive. I mean, when does this have an integer solution? Let's try to phrase this a better way, maybe. Let's look at that first example we looked at, the case where it was rational. Alright, so we first looked at log base 36 of 216, and we said, hey, that is rational. Okay, so based on what we just said, that implies that there are integers such that 36 to the a equals 216 to the b. Alright, and applying the prime factorization to each of these numbers, 36 is 2 times 3 times 2 times 3. So this is 2 to the 2a times 3 to the 2a. And that's equal to 216 is 2 times 2 times 2 times 3 times 3 times 3. So that's 2 to the 3b times 3 to the 3b. Alright, and from here we only get one equation, right? We get 2a equals 3b, and then again 2a equals 3b. So this says that 2a equals 3b, and so a over b equals 3 over 2, which is the value we got for log base 36 of 216. So if we look at this, we can see that what has to happen here is that the two numbers, 36 and 216, have to have the same prime numbers in their prime factorization, but that's not enough. They have to have the same prime factors in the same proportion. As we saw, that log base 6 of 12 is irrational because it has the same prime factors. 6 and 12 have the same prime factors, but not in the same proportion. 12 has one more 2 than 6, but it has the same amount of 3's. So that is the general result that we're looking for. Alright, so let's write the observation down. Alright, so that's our general claim here. For natural numbers m and n, log base m of n is rational if and only if m and n have the same prime factors in the same proportion. The proof of this is not bad. I'll leave it as an exercise. And as for the transcendental comment, when are these logarithms transcendental? Well, that's actually really interesting. It turns out